Yeah, and they're gonna be gone for a little while here. So, whoops.
They've been gone for like 3 weeks.
Yeah, we'll see them next year, basically. They'll be back.
Year?
Yeah, they'll be back at the beginning of the next year. Yep.
So they're gonna miss midterms. Yeah.
They will do they'll do midterms remotely.
Can you explain how midterms are?
Hmm?
Can you explain how midterms work?
How do they work? So actually I'm gonna go over it, but since y'all are both here and you're the ones that matter, let me get this rolling real quick and then I'll do that. They are both sick.
What?
Yep.
Are we the only people?
It's just the two of you today. I don't know. So I want to make sure this is open and running for them. They just Darcy had the flu and then
Lewis called the flu.
Lewis had like an antibiotic or something that didn't agree with him. That happens all the time.
I had the flu right on lesson before a lesson. Wait, what was that? One second. Was it lesson before? I just had a cough because the cabin we stayed at was so dusty that turned on the fan in the kitchen. It snowed dust. I got a flu on Monday, but
flu shot, you mean? Or
I just got I was sick on Monday.
oh, okay.
Tuesday I just got recovered for some reason. Mine in like a 24-hour bud.
Yeah, it happens. It happens. It's that time of year.
In my bathroom, I found like so much ants in the bathtub.
Oh no, that is the worst. I don't love that. They do that. I do not love it. It is not fun.
In my bathroom.
That includes. Yeah.
I found like a bunch of ants for some reason.
Yeah, they're not cool when they do that. That is not okay.
Thermal energy.
So we are doing thermal energy and heat, and I'm glad you guys are here because we're going.
We're going to learn about convection.
Yes, we are. Very good. And we are actually going to have a little demo today. As we're wrapping up, we're going to go out back briefly for a little demo, and we're going to do it out back because I don't want the other group to see it until we're ready to do it.
My birthday is exactly 2 days before midterm.
Oh my goodness. All right. Okay. So you asked how are midterms going to go? So let me tell you how midterms are going to go now that we're recording Zoom.
Midterm's really close.
Midterm is really close. Next week is review and then is midterm. So if you'll do two things for me, if you flip to the beginning of your binder, you'll find the preface.
Beginning of your binder?
Yeah, back at the beginning, right behind that with table of contents, you'll find that preface there. And then you see on that very first page, it says like grading scale. And then it'll say like weighting.
It says the final.
Yeah, not there. Flip back one more.
Midterm.
Right there. Okay.
Midterm is 10%.
Midterm is 10%. You see that?
Yeah,
okay.
Midterm is 10%.
So that means it's 10 midterm and final. Doesn't it say that too? It's say for final.
Midterm and final.
Okay, so that means together your score of your midterm and your final are 10% of your grade. Okay, so the average of those two is 10% of your grade. But all you'll see when you get your report card after your midterm is done, all you'll see is the midterm score because we haven't done the final yet, right? Okay, so here's how it works. It's going to be a very different kind of day. So flip one more time to the last page of this lesson. This quarter. So the very back of your binder, the very, very end. On the last page, you'll see right before that starts, right before that last lesson. Let's see. Right.
The October sky?
Actually, yeah, right before that, right after that. So it's lesson 16. Look at the page 1 for that. All right. Or 17. Sorry, I could say 17. Yeah, you're right. 17. All right, 17. So you see it says your midterms begin at 10:15 a.m. Okay. If you get here a little early, that's okay. All right. But you're going to want to come in, and neither of you have Miss Jackie, so you'll come straight to. I'll be at the counter. And I will have your midterm, and it's a little paper packet, okay? And there will be an envelope with it with your name on it. And there'll be a little sign, and I'll be there to tell you. But what you do is
orange envelope?
Yes. So you will take your envelope off of your little packet, and you'll hand the envelope to me, or you'll put a little bin up there. And then you'll take your midterm somewhere on this level of the house. So you can go to the dining room, you can go in there, you can sit in here, you can sit in the pub, wherever you're comfortable.
Can I sit on the stairs?
Sure. and you sit down with your pencil and you just work your midterm. And it's a test, but it's on paper and it's written. And there's some, got to write a couple paragraphs, got to answer some questions, you got to label some diagrams, and you'll do all that. And then when you're done, you'll bring it back to me. And then you actually won't be in the pub because the pub's the silent space. You'll have to go to the pub for silence. So when you're done, you go to the pub and sit in there, and that's quiet space. Yeah.
Will you practice like your whole from lesson 1 to lesson
Yeah.
15?
That's
And
next week.
after-
Yep.
Like on midterm day, will you practice from lesson 1 to lesson 15?
We won't practice anything on midterm day. You walk in and you take it. So
you
review is all
practice
next week.
before you go.
Yeah, oh yeah, yeah. We're gonna review next week, and you're gonna study.
Something. So like
What now?
mine's I was looking at the thing,
Mm-hmm.
the January March, bring something healthy.
Yeah. So you have to be creative. Come up with something that involves any of the concepts or scientists we've talked about. And I mean, you can honestly do like Newton's apple slices and caramel dip or something. That works, right? Like something like that. And you bring those in, and then we all eat lunch together and we watch the movie. Yeah.
Are all the questions in your lesson 16 midterm review?
Between that, Jeopardy, between those two, everything gets covered. Okay. So it might not all be there, but between that and Jeopardy, it's all covered. All right. So let's start this lesson because I want to be sure we have time for our little fun demo at the end. All right. So thermal energy and heat. So I have all my slides are little snuggy Christmas themed rats in front of the fireplace because that's nice and warm, right? That's what we all want this time of year. So thermal energy and matter. Yes, sir.
How like the question is like, why is there a build your own thermometer for lesson 15 lab and lesson 16 lab?
You had 2 copies?
Yeah.
You got your brother's missing copy. That's okay. You only should have one. There's next week's lab is going to be like a competition review. We're all going to be playing Jeopardy in teams. All right. So thermal energy and matter. Here we go. So what is temperature? Temperature is the average what? What is it, Eunice?
Temperature is the average kinetic energy.
Yes, it's the average kinetic energy. And what's kinetic energy? Do you remember what kinetic energy is, Emma?
That
Yeah, what is it?
energy would be the energy that's like currently being used.
Yeah, motion, energy and motion. So when you think about temperature, you think about it as how hot something is, but it's really not. It's the average of all the motion within something, all the motion of the particles that you can't see. That's what's causing it to feel warm or cold. And really what that is heat. What you're feeling is heat. And we'll talk about that too. So thermal is the total of all of the particles, the movement of all the particles. So there's particles in everything, right? Even though we can't see it, there's particles in gases, liquids, solids. All right. So what's the transfer of thermal energy? What's that, Eunice?
The transfer of thermal energy.
The transfer of thermal energy from one object to another. What's that?
Is it temperature?
Not temperature. Temperature is the average heat. Very good. Okay. So like if you touch that table in front of you, does it feel cold, warm,
Normal?
kind of normal? How does it feel compared to the couch or the chair?
It looks a bit colder.
It feels colder. Well, here's the thing. Both the couch and the chair are 67 degrees because that's the temperature it is in here. The reason the table, both the chair, couch, and the table, they're all 67 degrees. The reason that feels colder is because glass is a better conductor. So it's pulling the heat from your hand, which is why it feels cold to you.
So glass pulls more heat
Than fabric. Yeah, fabric's an insulator. That's why we use it for blankets.
Like a fabric ice pack might feel cold, might feel warmer than a
Yes.
ice pack, even though it's like the same temperature.
Yes, exactly. Yes. All right. So we'll talk about that in a minute too. That's about insulators and conductors. So thermal contraction and expansion. So what is the increase in the volume of material due to a temperature increase? Do you know, Eunice?
Contraction?
Not contraction, but
Melting?
not melting. It's the opposite. Increase in volume. So a decrease would be contraction, but an expansion is the increase, right? So when you get something warm, most things, when you get them warm, they get bigger, right?
Yeah.
They spread out.
If you're putting marshmallow in a microwave, it would be too
Yes,
big. but then when it's cold.
And why is it doing that?
Yeah.
What's causing it to get bigger, do you know?
The
You
heat,
know?
because maybe the molecules are like moving really
Mhm.
fast and it's pushing it away. But because
Yeah.
the molecules start to cool down, it kind of moves less.
So what's a marshmallow made of? Do you know?
Sugar.
Sugar and what else is in it?
Sugar and
Why isn't it crunchy?
because
Like a lollipop.
it's made of
Why is it squishy and spongy? What else do you think could be in there? Sugar and what?
milk.
Air. Lots of air. So when you heat it up, it's the air that's expanding that makes it go inside the microwave.
And then when it
Yep.
gets smaller, the air is kind of leaving it.
Yes.
And it's
Right. And it comes back down to normal size.
hard because
Right. So sometimes in science we talk about specific heat, and specific heat is basically like it's like a material's capacity for heat. So it depends on the material, and it's the amount of energy required to raise the temperature of a material by 1 degree Celsius, so that it's different for every material. So as the thermal energy of substances increases, its particles spread out and the substance expands. So thermal expansion is an increase in the volume of material due to temperature increase. Matter expands when it's heated, and this is why this is what makes liquid in thermometers rise. So that's what we're going to do in lab today. And it's the reason for joints and highway pavement. You know, when you ride along the highway, you're on the interstate and you hear your car and you kind of feel it too, it goes. You ever felt that? There are little rubber strips in between the concrete sections on a highway, and they're there because that concrete is going to expand. And if you didn't break it into chunks and put the rubber strips in between it, it would just crack. So those little rubber strips.
When you're like in a parking lot, there's little cracks.
Oh, and they fill it with that rubbery stuff. Yeah, that's tar is that's how they fill it. But yes, that's why it cracks. A lot of it is because it's hot, or because it's the stuff they pave parking lots with isn't as durable as the stuff they pave the interstate with. So it just gets beaten up. Yeah. What's the next one?
Thermostats.
There you go. So thermal expansion is also using thermostats, many of which contain bimetallic strips. So this is especially how the old school ones worked. So a bimetallic strip is made of 2 different metals which are joined together. So this means they expand at different rates because their specific heat is different. If one side expands faster than the other, the strip will curve and operate a switch. So we're going to watch this. Now, first, rule for life. Rule for life. Never speak ill of Mr. Wizard. His name is Don Herbert, Mr. Wizard, who was on television in the 80s. He's definitely one of my childhood heroes. I love this man. There is absolutely nothing strange about random neighborhood children visiting a grown man's home all alone to learn about science stuff, which they did. They just random neighborhood kids popped in and he taught them about science. And there's nothing weird about that. It's totally normal. You go to your old neighbor's house and learn science, right? Totally normal. It's just Canadian. That's all. So he's going to show you how thermostat works right here. That's true.
Neighbor-ish.
But at least you all go together. This is like just kidded one at a time.
This, I assume, Dan, right?
Yeah, it's a thermostat that you put in your house to measure the temperature of the heat.
Well, you not only measure it because there's a little thermometer here, but it actually turns the furnace on and off, right?
Yeah.
Well, you and I are going to investigate what goes inside here. And it's based on the idea of bimetal strip. Bimetal meaning, what do you know what bi means? Two, like 2 metals. In fact, here are 2 metals right in front of you.
Yeah.
There are 2 wires made of metal. And I'm going to send electric current to them to heat them up.
Okay,
You get down and sight right across those weights that are on the top there.
okay.
And watch what happens when we heat up the 2 different metals. What's that?
Well, the one in the front is sinking down, though. It's pretty much going down.
Now watch, I'm gonna turn off the current. Go back up again. As it cools off, it will go back up to the same height as the other one. In other words, what I did this for was to show you that metals expand, but different metals expand at different rates. Obviously, the one on the front expands the most. Okay, now let's assume, I'm right over here, and light the candle. And let's assume that we take 2 metals and put them together to form one strip, which is what this is.
Okay.
Light the candle. Okay. You can put it right down there. Now hold the strip right in the flame of the candle and watch what happens.
It started making an arch upwards, it's making a really
The arch
big.
going up?
Look how it's bending.
Yeah, there's a lot. All right.
Because of the heat.
Okay, now you can blow out the candle. Okay, now what happened is we have, that looks like one metal, but it's actually two metals put together, like these two pieces of wood.
Okay.
Okay, now watch what happens if I expand the bottom. Watch what happens to the whole thing.
Oh, it's making an arch upwards.
It's a go up, and that's why that went up,
I see.
because the bottom piece of metal expanded more. Now let's assume we take this piece of metal and form it into a coil.
Okay.
To go around over here, I have a thermostat all set up on this little piece of wood. Can you find the coil?
Oh, there it is, I think.
Yeah,
It's close
That's
up around there.
There's the coil made out of that bi-metal. And at the moment, notice that there's no current going to the furnace represented by this light bulb. Okay. So we want to cool off the room in order to make the furnace come on, and you do it here with this spray. Go ahead. Push down on the top, and out will come a spray of gas, and you will cool off the coil. There you go. On to the furnace, right? Okay. Now this is the furnace. So turn on the blower and hold it at the top. Okay, now the furnace went off.
Yeah, it's right off.
Now, this time let me handle it, because I want you to watch right there, right at the end, see I put a pointer here?
Yeah.
Right at the end of the pointer, watch right there. Right now, that's a switch, and it's open.
Okay.
Watch what happens when I cool it up.
Wow, the switch moved down towards here.
Right. And
Expanded.
made it connected, right, made a connection, and sent current over to the furnace, which now comes on. Now watch what happens to the switch.
It moved up again when we turned it on.
So now.
That is cool, isn't it?
That looks, what do you call the thing inside? Line, smell, line.
There you go. So that's how thermostats work. And it's taking into consideration the specific heat of the two different metals, right? So, yep, Master Wizard, we know. So, like I said, totally normal to go to some strange man's house and learn about science. Childhood hero, totally amazing. All right, so we measure our temperature using different types of scales, right? And they all have a different purpose. So this is what they are. So we in the US tend to use Fahrenheit a lot, right? When we do our weather reports, or even when, people say, do you have a fever? We're usually using Fahrenheit, which is an older scale. Celsius is the one we use in science, right? Because it's our metric one. So yeah, Celsius is metric. So we use Celsius. Kelvin is very rare, and actually more than that, or the Rankine and Réaumur, those are very rare. Kelvin is used a lot in physics, and it's used a lot in physics because Kelvin takes into example, you see this right here, 0 Kelvin? Okay, this is 32 degrees Fahrenheit right here. Yeah, that's where water freezes, okay? And that if you look right here, 0, that's where water freezes. So look along here. See this line right here?
Yeah.
This line right here is where water freezes, right? So
3.15 Kelvin.
yeah, that 273 degrees seems hot, right? Because 0 Kelvin is a theoretical temperature at which all motion of all particles stops. So if you talk about temperature by its definition, which is the average of all average motion, average kinetic energy of all the particles in a substance, that's what temperature is. So if you want that to be 0, then the particles all need to have 0 energy, right? So that's what Kelvin is. So Kelvin is used more in physics than in other subjects, but it's really cool to know about it. And there's, we'll talk about it a little. So Fahrenheit's used mostly in the United States. Water freezes 32, boils at 212. And let's see, here's boiling right here along this top line. That's boiling. So 373 Kelvin. You can also see that like this range goes from 0 to 373. This one goes from 0 to 671. What do you think would be, like, compare these two? Actually, compare, let's see, compare Fahrenheit, no, compare Celsius to Rankine. So if you look at Celsius, negative 237 to 100 is what's on here. And then this one is 0 to 671.
Wow.
Yeah. So what my point that I'm trying to make is that in some cases, the actual, like how do I want to say it? The steps between the degrees are either bigger or smaller. So it's either more granular. It's like, are you measuring in, it's sort of like how some things you would use centimeters for and other things you would use meters for, except they don't directly, they don't convert easily like Celsius converts. Celsius is, I mean, sorry, when I say Celsius, metric converts. So there's a little math involved in converting one to the other, or you can just look at something like this. But you can also use online calculators where you can say like convert whatever Celsius to whatever Kelvin, and that'll happen for you. So Celsius is pretty much everywhere else in the world except us because we have to be special. And Celsius is, yeah, Celsius makes so much sense. 100, 0, water freezes, water boils, right? And then Kelvin is used in physical sciences where water freezes at 237.15 and it boils at 375.15.
I noticed that in some of these, there's a point two, then there's two number after the point. But
Yeah.
in ours, we only have one.
Yeah, that's because that's what I'm saying about some of them are more granular than other. So like, and this is exact, like basically what they're doing is they're using Celsius as the benchmark here and they're converting everything else to Celsius. If you had used like Rankine as the benchmark and say instead of putting in 558.27, you just put in 5.5528, then the others would have decimals, right? So you can tell that this is the scale they're using in order to come up with the conversions for the others. All right, so yes.
Can you go back to the
Yeah.
page?
Mhm.
Is it the last one, the blue one? It says Riamer.
Mhm.
Is it a Spanish word? Or
I think it's French.
or French?
Yeah, I think it's French.
I've never heard. I've heard a bit about Kelvin. I know
Yeah.
about Celsius, and I know about Fahrenheit, but I haven't heard.
Yeah, those other two are just not super common. They'd be for very specific tasks for specific
So basically
disciplines.
non-existent.
No, just not used as you probably won't come across it. So specific heat, we talked about this one already. So this is the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, so that is that's how we define specific heat. So this is the specific heat in joules per gram of various materials. So like we have granite on here, and then we have water on here, and we have lead on here. So we know basically it's sort of like what amount of energy is required to cause a shift in the kinetic energy of the particles within those particular materials. Okay. So calorimeters, calorimeters are something that use a principle that heat flows from what to what? How does heat flow? Always. Do you know there, Eunice?
From the hotter things. From
Yeah, Emma's got it. From hotter to colder. Yeah, so you've got hotter to colder until they both reach the same temperature. This is like, remember when you touched the table a minute ago and it felt cold? It feels cold because your hand is hotter and the heat is moving from your hand to the table. You have more, your temperature, if your hand is greater, you put it on the table and it's pulling heat from your hand into the table. And that's why your hand feels cooler. Sooner or later.
Put your hand here. That means this fabric material. Won't.
It does get warmer. It's just not as obvious and it would take way longer, right? That's why, like, if your hands are cold and you go over and you put them on something warm, they're going to warm up much faster.
Like someone else's body, like
Yeah, or a hot water bottle, or right? Yeah, much warmer than if you just, much faster than if you just stuck them on the counter, right? So heat and thermodynamics. All right, so thermal energy and states of matter. So this is like, sorry, no, I just knocked the picture over with my hip or whatever, ankle, something. All right, so states of matter. This is like back to our first couple lessons. We talked about states of matter, solid, liquid, gas, right? Okay, a physical change from one state of matter to another. What do we call it? Eunice, what do you call it?
physical change from one state to another. It's called it's called conduction.
Nope, this one's easier than that. It's change of state. Yeah, as well, because it's a state of matter. So we call it a change of state. So matter will change from one state to another if thermal energy is absorbed or released. So picture an ice cube in your head, okay? And you put that ice cube in your hand. What is going to happen to the ice cube?
The heat from your hand is gonna get transferred to ice.
Right, and then what happens to the water that the ice cube is made of? It's
it's gonna
currently, yeah, it's in a solid state and it's going to go from solid to liquid. So it says that it'll change state when thermal energy is absorbed or released. So what's happening there? Is thermal energy being absorbed or released by the ice cube?
Absorb.
Yeah, it's absorbing thermal energy from your hand, so it's changing state from solid.
Releasing the heat in liquid.
It will, no, if you go the other way, if you were to freeze it, it's actually releasing thermal energy to get into a frozen state, which you don't have the power to do by sticking it in your hand. But if you're gonna freeze it up. Mhm.
Yeah, or I guess because.
Yeah, if you've ever, for example, like I work with cakes and stuff, so sometimes I work with hot sugar. And if you ever accidentally get hot sugar on you, it will go from liquid to solid pretty fast because it's releasing a lot of thermal energy. And where do you suppose that thermal energy goes if you pour hot sugar on your finger by accident?
In your face.
Into your finger, yeah, that's why you end up with a big old blister or something. Yep, that's how it happens. Same thing. Okay.
Yeah, that happened to you a lot.
Oh, many times. Oh, yeah. It's just, part of the job. All right. So now we talk about convection. Okay. We're going to talk, like you said, convection, conduction, radiation. All right. So the transfer of thermal energy when particles of a fluid move from one place to another. What's it, Eunice?
Convection.
That's convection. All right. So convection is when it's moving from one place to another. Okay. Convection currents. What did we remember when we did that little earth science bit at the beginning of the year? What happened with convection currents? Do you remember what we talked about with them? We brought it up. So back when we talked at the beginning of the year about plate tectonics, do you remember?
Yeah,
Like,
tectonic is the theory of the plates.
right. And what was the driving force for plate tectonics? Do you
The
remember?
continental drift.
Yeah, that's what's happening.
Well,
it's continental drift. But what was causing it? Do you remember? Here's your clue.
Convection current.
Yeah, where are the convection currents on Earth that are causing
The
the?
plates.
Yeah, it's the mantle underneath, right? Remember all that molten rock in the mantle? It gets really hot, and hot things. You think of heat rising. Really, what it is isn't heat rising. It's that things that are cooler or more dense and they sink, and that pushes the other things up, right? So you've got the rock that's reached the top starts to cool. And then it sinks to the bottom and pushes the other hot rock up. So what you get is this circle going round and round and round. And remember that rolling motion is what caused plates to move, right? So convection currents occur when fluid circulates in a loop as it heats up and cools down. So fluid can be a liquid or,
Yeah.
yes, a liquid or a gas. They're both fluid, remember? So convection currents are important in many natural cycles. Ocean currents is a good example. Weather systems, and then there it is. Hot rock in the Earth's interior, right? Okay, radiation. This is the transfer of energy. We know what it is there. It's transfer of energy by waves moving through space. All objects radiate energy. As an object's temperature increases, the rate at which it radiates energy increases. Now, when you come back next semester, one of the first things we're going to talk about is the electromagnetic spectrum. And we'll be talking about radiation a lot there, okay? But if you were to, if Yusuf was to put his hand over there on the back of the couch and it felt nice and warm because the sunlight coming through, that's radiation, okay? Now, our last little picture here to help you see these three things. So what's going on there? It can be conduction, it can be convection, or it can be radiation. So conduction is when you touch it, okay, and it moves. Radiation? Okay, well, let's see what it is. Okay, so what's going on there is radiation, transfer of heat energy by waves moving through space. So there's heat under there, right? You see the fire. You ever looked at a fire from the distance or whatever, and you've seen how the air above it looks wiggly? Yeah, because it's distorting the way that the light is cutting through all those molecules in air, right? So you get this transfer of energy by waves. So that is radiation. Now, what do you suppose is going on in his little pot of stew?
Is it convection?
Convection, yeah. So what happens is it'll start to get nice and warm in there, and that stew will bubble up to the tippy top. And as it starts to cool off, because it's in contact with the air, it'll sink back down. It pushes up the next round of stew, and it goes round and round and round. And our lava lamp, that's your convection too, right? Up and down, same concept. So there's your convection. So it's the transfer of thermal energy when particles of a fluid move from one place to another. Convection current is when fluid circulates in a loop and it heats up and cools down. So then lastly, why is he wearing little pot holders?
What?
Why is he wearing little pot holders, little gloves on his hands?
So it like blocks the heat.
Yeah, so what would happen there if he wasn't wearing them and he just touched that hot pot? He would get a blister, and that's because of induction. It would go straight through from one object to another. So if you look in your review slides, you'll find an image in there somewhere. It's a little pot on a campfire.
Like this.
That's the one. Can you show that to Emma real quick?
I have it in mind.
Okay, yeah, you see that? Okay. That right there, keep that in your head and memorize that image. It may just show up on a midterm.
Conduction.
And radiation. That
By tests. And
Yeah, and it may just show up on a midterm. So you remember that because that's important for all things. Yeah.
By the way, in the unit 4 and 5 tests, it was like so easy because everything got matches like lines and stuff.
Oh, I needed to shuffle it. No, thanks. I'll have to shuffle it. Okay. So for some reason it came unshuffled. Using heat. All right. So now we know all this about heat. How can we use it to our advantage? Well, let's see. Heat engines. All right, so two main types of combustion engine are external combustion and internal combustion engines. This is a chunky Santa rat. Look at his cheeks, right? Okay, so what kind of engine burns fuel outside the engine? Outside the engine. What do we think? Do you know, Eunice?
Insulator?
No. What kind of engine burns its fuel outside? Okay, so let's look back at this steam engine. Yeah, steam engine's a good example. Okay, so this is an external combustion engine because you put the wood or the coal into the burner and it burns and it heats water, and then the water moves things and that causes the pistons to go and you get the steam coming out. So that's external. Internal combustion engine burns fuel inside. This is what happens with your cars. Okay, if you drive a gas powered car. Okay, and this is going to be our demo in just a minute. We're going to come back to this topic. So remember, internal combustion engine burns heat and uses heat inside the engine. It's burning the fuel inside the engine, and that's using that heat to move the engine forward. And we're going to do something really fun with that in a few minutes. But first, let's wrap up the lesson. So heating systems. So what heats rooms in a central location? What do we call that? Do we know? What do you get, Emma?
A space heater?
Yeah, space heater can be one, or central heating. So a space heater would do like one room. Central heating is probably what you have in your house. It's when you touch the thermostat and the heat comes on in all the rooms. That's a central heating system. They call it central heat, central air. Okay. So most heating systems use convection to distribute thermal energy. So you remember how how Mr. Wizard showed us how that thermometer worked? And so like if you're in a room and the room gets cool, right, then it's going to kick the heat on. Now, very smart. When the architects that built this neighborhood, when they built this house, they did something very, very, very smart. There are 0 thermostats and 0 vents to put air out. There's an intake, but no blowing type vents in my foyer upstairs. So let's think about this. If it gets really warm down here, what's going to happen to all that warm air? Yeah, it rises right up the stairs to the tippy top, right? If there was a thermostat upstairs and it registered, oh, it's really hot upstairs, I better turn on the upstairs air conditioner. Is that going to help anybody down here?
No, you're gonna freeze.
Right. So there's nothing in that. You'd be hot down here because the oven's on, whatever, everything's hot. So they were very smart in not putting anything in there because that area of the house is different architecturally, right? It's 2 stories high. So it's helpful that there's nothing in there, and it doesn't blow either.
Intake.
There's an intake just to kind of pull air through to recycle, but there's nothing blows and nothing gets measured in that part of the house. So it's very smart. So there are different kinds of heating systems. There are hot water systems, steam engines, electric baseboard heating, and forced air. Most of us live with forced air. That's when it blows. Like if you have vents like the ones on the floor or the ones in the ceiling where it goes, when you feel it blowing into a room, that's forced air. Baseboard is really cool. It's under the floor and they have like heating, like kind of like, your back window of your car has those tiny wires in it and it can defrost the window. You ever seen that? It's like that, but it's in your floor. Radiators,
That's what the black little line.
yeah, that's what they do. They're wires. They get just a little hot, just hot enough to melt frost. Yeah. Now, radiators, that's what he's doing there. You see him with that mallet? Okay, that's because radiators get bubbles of air in them and then they bang and make incredible noise. In college, I lived in a house that was built in the, I think it was late 1800s or early 1900s. It was an old house. And it had radiator heating, came from a central boiler on campus, a big room that boiled water sent through pipes everywhere to heat all these old buildings. And that radiator would go bang, 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 bang. And I had a rubber mallet. I would smack it till you move the bubble enough and then it stops making noise because it'll wake you up in the middle of the night. It's so loud. So cooling systems. So these are they reverse the normal flow of thermal energy. So a heat, what does is, let me just click through these because I want to have time. So heat pump reverses the normal flow of thermal energy. And that's a device that some people have in their houses. And refrigerant is a fluid that vaporizes and condenses inside of the tubing of a heat pump. Your refrigerator is a heat pump. Sounds weird because the word heat is in refrigerate, but it's a heat pump. So what it does is it basically uses a refrigerant that goes through some coils and it condenses inside and that
Is this a
pulls
picture of
of coolant. Yep, there's a picture of how it works, right? So lastly, air conditioners remove heat from the air. They also remove humidity from the air because water in air will hold more heat than water. This is why, have you ever been to the desert and people say, oh, it's a dry heat. But like in the desert at night, it gets really cold. There's less water in the air, less humidity to hold heat.
It's a surviving challenge, and then on the desert it was like
Mhm.
112.
Yeah. Okay, we're gonna take this outside. We're gonna go on the back deck.
It could technically snow.
It could. Mhm. So we're gonna go out here. We're gonna do
But
some.
But it's
Right?
that it became more maybe or probably.
Let me get a. No, you don't need your binder. You will need. Let me get it to stop sharing real quick because I don't want to. Do. Stop share. Where is it? Oh, stop share. Stop share. All right. So here, I'm gonna put this right here so we can see it. All right, Eunice, you need glasses. Emma's got glasses on. All right, so
Yeah,
let's do this.
I don't need my.
Oh, you have them on?
glasses.
You put them on. I didn't even know she put them on. Okay, so we are going to take a second here. Now,
I just
we
say
talked
good-
about combustion engines, right? Right?
I don't need them
We
on.
talked about internal and external. You will in a minute. I'll tell you when to put them on. Okay?
I wish I had my. Okay, it's kind of cool.
Yeah, we won't be long. All right, so we're going to show you first and foremost this right here. All right?
I see gasoline.
You do see gasoline, and these are matches. Okay? So here's what.
big matches?
They're big, long matches. There's a reason. Okay, so step back a little bit from the table if you would. All right, I am going
Now do we
to
need
take
our
this.
glasses?
Not yet, I'll tell you. Well, you could put them on if you wanted, but all right, I'm going to take this gasoline and let's just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, 10's good. We don't even need that many. What's going to
Wow.
happen if I light this match and touch that?
It's.
What do you think?
Boom.
You think it's going to boom?
Or maybe not boom, but it's definitely gonna burn.
Okay, we got
Probably it's
burning.
gonna expand.
So let's watch.
I don't know.
So we're just burning. Burning away. Now let me ask you, is that producing enough energy, you think, to move a car forward?
Yeah.
But it's gasoline, it's what you put in a car, right?
Yeah.
So what's gonna make a car go how is that gonna make a car go forward? That's not a lot, right?
Yeah.
Okay, so we're gonna do something a little different. Cars use cylinders, okay? In your engine is what's called a cylinder, right? This is a cylinder, right? Y'all agree it's a cylinder?
Yeah.
Yeah, it does smell good. See this little hole?
Yeah.
Okay. I'm gonna take advantage of this tiny hole. All right, now this little guy here, I'm gonna move him off. I'm gonna take him over here and I'm just gonna kind of,
Ew, the smell.
Squish him out.
stinks.
now you need to step back and be sure your glasses are on, okay? Because now we're going to see. This is how car engines actually work. So I want that to get wet. We're gonna take this little can, okay? And we're gonna, how many drops did we put on that one?
10.
10. Okay, well, I'm gonna put 10. I'm just gonna put
5.
I'm gonna put 5. Let's put not even 5, maybe 1, 2, 3, 4. Oh, let's be generous. Let's go to 5. Okay. Now,
Yeah.
they're just sitting in here, right? They didn't absorb into anything. They're just sitting in here. I'm gonna put the lid on. Okay, this is a smaller cylinder inside of a larger cylinder. Okay, so that's what is in your car engine. All right, so y'all would just stand back for me. Now, I put that in there and I twirled it around a bit, right? Step back there, Eunice. Whoop, wind. The wind doesn't like me. Stop blowing, wind. You're messing up my experiment.
I think the matchstick got wet.
Okay. Oh, shoot. Come on.
I think
Oh, it's the wind. Okay,
we
wait a
should
minute.
have.
Wind died down.
Let me wear my
No,
goggles.
no, no, wind died down. Put your goggles on. Something. Wind died down. Ready? Oh, come on. Do your thing. Oh, you're failing me.
How
Now,
much
come on.
matchstick
Yesterday
do you
it went kaboom. So hang on. Oh, I have a lot of matchsticks. Let me make sure that there's actually still, we didn't evaporate out.
Thankfully, you have a lot of them.
Yeah,
Maybe
yeah.
wearing gloves to open it.
Nah, there's nothing really to hurt me. I mean, I put gas in my car every day and I get gas on my hands when I do that. It just smells bad. I think it all evaporated. Well, that's the point I'm making. Little failure there. Is that 1, 2, 3, 4, 5. There we go. Is that when you do this, it vaporizes, right? And the vapor, I gotta trap it. All right, step back. The vapor is what you need. Okay. Oh, son of a gun. Look at this. That's not functioning today. Would that move a car forward?
Yes.
Okay, so that's how it works. That's how internal combustion engine works on a very tiny
Oh.
scale. Look. Boom. And this is, if you touch it,
Wow.
you can feel that it's very warm. It's not too hot. You can touch it. You feel that it's warm?
Yeah.
It's warm, people at home. Okay. So there's that. How was that for your last lesson of the semester?
That was nice.
It was fun, right?
Yeah.
Kaboom.
That was so fun.
Yeah.
Are we gonna do this on lab?
No, we got a different stuff for lab, but I wanted to
Oh,
be
no.
sure that I had shown y'all that. I'm gonna take these in. Make sure everything is set for my next group of peeps.
Boom.
We're all good. Okay, you can put your goggles on that thing. I'll take care of them. And I'll close out this lesson. Perfection. Thank you, Ms. Emma. Whoops. There we go. Thank you, sir.
Are you done?
We are done and ready for lab. Yeah, now I will leave this, I will put this up for you real quick. Let me share this screen back over for just a second. You got about 5 minutes. Let me put up your study guide stuff, okay? Hang on one second. Yes, of course, but hold on one second. Let me put this up. So make sure that everybody at home sees this. So we've got, I will leave this for you guys to watch. It's not really part of your lesson. It's just extra. These are the topics for your exam. Got it? Looks like Eunice already did it, so he's good to go.
Yeah.
So you're done. So those are the topics for your review. And let's see, I think we have enough time, actually. I'll let you guys see. I was supposed to put this there. I'll let you guys watch this.
Mistakes. I got 21.5 out of 23. And the only mistake was what's the SIU for Jewel. I actually put work instead of work.
Oh, I always go back and check those, you know. All right, so here we go. This is what we just saw. I'll put this back outside.
You would have a two-stroke engine. If you observe the anatomy of these two engines upon first glance, they seem very similar. They both have a crankcase and a crankshaft get a rod. As well as a whip fin and a piston.
What is this? I don't remember. Oh, this is a cool type of.
They also both have a cylinder.
Work pop like how we pop.
And they both operate by concurrent occasion of the piston. It's a location of the crankshaft that defends strength the use of the transmission and ultimately the wheels of the vehicle. But beyond these core similarities, the four-stroke and the two-stroke start to fundamentally diverge, resulting in two very different approaches to internal combustion. And what I'm going to do today is give you the only video you need to watch to get a very solid understanding of how a four-stroke and a two-stroke engine work. We'll also be exploring the differences, benefits, and drawbacks of each engine type. And this will then answer the question of why the four-stroke ultimately prevailed over the two-stroke in most applications, despite being larger, heavier, more expensive, and more complex. So with the four-stroke. Why is it called a four-stroke? It's because the four-stroke engine needs 4 strokes to complete one combustion cycle. Any time that this moves from top to bottom, and vice versa, that's one stroke. One stroke of the piston equals 180 degrees of crankshaft rotation. Now, the 4 strokes are intake, compression, combustion, and exhaust. During the intake stroke, the piston travels from top to bottom, which are also known as outlet center and bottom center. As the piston does this, it creates an empty space or vacuum inside the cylinder. This newly created void is essentially a brief absence of air. And because we have an absence of air, we also have an absence of air pressure. In other words, we have air pressure inside the cylinder and atmospheric air pressure outside the cylinder. This air pressure difference cannot continue to exist, and air naturally seeks to equalize pressure everywhere. And so air, together with fuel from the outside, will propagate into the cylinder and fill it with a fresh air-fuel mixture. By the time the piston reaches bottom dead center, all the air and the fuel that can hope to get in have done so, and the piston now starts to move upward. As it does that, it forces the air-fuel mixture into an ever smaller space. In other words, it's compressing the air-fuel mixture, which is why this stroke is called the compression stroke. Just before the piston reaches top dead center, the spark plug fires and ignites the air-fuel mixture, which finds itself between the 2 electrodes of the plug. Although combustion inside an engine is often described as a bang or explosion, that isn't what's actually happening. An explosion is detonation, which is a rapid, uncontrolled process. In contrast to this, combustion is deflagration, which is a much slower, more even, and controlled process. Combustion spreads out evenly outward from the spark plug through heat transfer. The small portion of air-fuel mixture initially ignited by the spark plug heats up and ignites the next layer of the air-fuel mixture. This layer then ignites the next layer, and the process continues.
So you can finish watching it at home, because we're gonna start lab, but I wanted y'all to have that, so you can watch it and see, because this is how your cars work.
I'm gonna go.
You heading out? Hey, break a leg. You need your, break a leg, break a leg. All right, so I'm gonna end this for my folks at home.
So long.